All right, up until now, we've looked at these general time and transfer constants. We've looked at how you calculate all these coefficients, B1s and B1, B2, B3, all the way to Bn, and A1, A2, A3 to Am, using the generalized time constants and transfer constants. The time constants being tau I, superscript j, etc., and the transfer constants being Hij's. Now, one of the interesting things that happens, and we've talked about this implicitly, we've used the result, but we haven't really formally proven it or shown it up until now, is the effect of uncoupled poles and zeros. And where do they come from? You said, we made an argument that's saying that if there is a time constant, or more accurately, uncoupled time constants and uncoupled transfer constants is a more accurate way of talking about it. If there is a time constant that does not change, no matter what you do to the other reactive elements, let's say the time constant associated with reactive elements n does not change when you short circuit or open circuit all the other ones. No matter what you do to them, it remains the same. We call that an uncoupled time constant. And we argued that that's going to be actually corresponding to a real pole. So now we can actually see where that comes from. And it's not that complex a proof, but we'll choose. So in general, so we are talking about uncoupled. And I use the word uncoupled on purpose instead of decoupled, because they're kind of slightly uncoupled time constant. Time, and then we talk about transfer constants. So we know in general, and this is a very important observation, that if you have a time constant tau I 0, it could be 0 value or non-zero value, in general, this is not true. It does not, the time constants do not, there's not a one-to-one correspondence to the pole frequencies in general. And there are several different ways to see that. Obviously, the number of time constants and poles is not always the same. Right? You have a capacitive loop, things of that sort that you can reduce the number. Poles can be complex, time constants are real. So obviously this cannot be generally true. Right? So, but now let's assume that you have what we call an uncoupled time constant. So uncoupled time constant, what do we mean by that? It's defined as a time constant whose value is the same, so let's say whose zero value, so let's say element n. Let's say we're talking about element n. So element n, where it's zero value time constant, if its zero value time constant is different from its time constant with I infinite valued, or with I and j infinite valued, or any combination of I, j, k, etc., if they are all equal, meaning that this time constant does not change, the value of this time constant does not change, no matter what you do to the other elements, short circuit or open circuit them, for any combination, and we can call that value actually just simply tau sub n. Right? So we define tau sub n as that value if that value doesn't change. Now if you have something like this, then let's see what the denominator looks like of the transfer function in general. The transfer function in general, of course, the denominator of the transfer function is of this form, right? b1s, b2s squared, etc., right? Now, if you look at this denominator, let's call it d of s, it is written as this sum, but this sum can also be, so this is 1 plus b1s plus b2s squared plus all the way up. What is b1? So we can write it as, we know b1 is the sum of the zero value time constants, right, from 1 to n. So it's tau I zeros times s. And so that's b1, b1s, right? We agree that this is b1. And then we know what b2 is, right? So it's s squared times b2, which is the double sum over ij, I smaller than j, smaller than or equal n, greater than or equal 1. So all the permutations calculated one way. You don't go for ij and ji. Of tau I 0, tau j I. And to higher order terms, s3, s cubed, etc., right? So if you have this, now we know one thing. So we can actually now spread this a little bit. So now we can rewrite this slightly differently. We can write it as, so I will take the nth term out. Right? the last term of the sum. So what would it look like? So I will take that out. So I would get s times tau n0, which is the nth term, plus whatever is left, which is s, times sum over every other term all the way to n minus 1. So it's I from 1 to n minus 1, tau I0. Right? And similarly here, what I can do, I can take the one that corresponds to the n, right, over there, and I can take that out. So I basically will have tau s squared, so we'll have s squared tau n minus 1, because you won't have n. And then there would be still one of the sums left, would be the sum for I, from I equal to 1 to n minus 1 of tau I0, right? So that's the one corresponding to the n term. And then you will have whatever is left, whatever else is left, which is all the sums to the n minus 1. So it would be s plus s squared double sum of tau I0 tau ji. ij, I smaller than j smaller than n minus 1. So this becomes n minus 1 instead of n, because I've taken that nth term out, which is this guy, plus higher order terms. Right? But now you can actually see what's happening. So now if you actually have this condition, meaning uncoupled poles, this is the same as this. Right? Because they're all tau of n, element n, with different things in the superscript, meaning that different things are infinite valued. But we said for every combination of things that are infinite valued in the superscript, they're all the same, if that was the condition, right, for this thing. So if these are the same, one thing you can actually notice is that now you can do a regrouping. So now you can take these two together and write it in general as that. So we can write it as 1 plus s. Now I'm going to write it as just tau n, because we said if this, so this is the assumption of being uncoupled. That's where it enters the equation. Tau n, okay, plus then you have here, between these two, what do I get? I have an s, right, times, or let's write it this way. I have 1 plus s. Now, tau n minus 1 is also tau n. This guy times, and I've factored basically this sum out, times s sigma I 0, 0 value time constant from 1 to n minus 1, and so on and so forth. So actually you will see that there would be the last term from the sum of the higher order term would come back to this one, and it will repeat itself. So the next one will also have a term 1 plus s tau n times a higher order term. It doubles. And so on and so forth. So you can see every single one of them has this term, which basically means that you can factor this term. And if you factor this term, you will have 1 plus s tau n times what? So you will have a new set of a's and b's, and so let's call it b1 prime s plus b2 prime s squared all the way. And b1 prime is just some of the zero value time constants for all the other elements except for element n, which is taken out. And this is also a double sum all the way to elements n minus 1. And so on and so forth. Which basically means that now the denominator can be factored. Which basically means that now in this special case, there is indeed a pole. So there is Pn at 1 over negative tau n. Negative 1 over tau n. Right? Because this is now a factor. Which means that you can basically factor this out. Yes?
Aren't you missing an s squared with the double sum?
Yes. I am missing a s squared here. Thank you.
And then on top, I think it says squared times the double
Yes, this is also S squared. Thank you very much. Yes. Thank you for the correction. Yeah, so that's good. Yeah, but the end result is correct still. Okay, so you can see it, you can see factor it. Now, this can be generalized, actually. So this is the general form, and I'm not going to prove the generalized form, but you can actually easily see it. I'll tell you how you prove it, which is just a little bit more mess, but the same kind of result, which is that you, in general, your time constants are partitioned into clusters, meaning that there are, if this is the space of all of your time constants, all taus, okay? So you may have a single one, let's call it tau 1. This is an uncoupled one, like this one. You may have a group of 4, tau 2, tau 3, I don't know, group of 3 here, group tau. You may have a group of 2, and you may have, I don't know, group of something else, some other groups that are collectively coupled to each other, but they're uncoupled from the other groups. This corresponds essentially to polynomials of the form. So this one will give you 1 plus tau 1s, means that these can be factored in these forms as time constants. Now, any polynomial with real coefficients, right, can be factored as first and second order terms. But the question is that can it be factored in terms that are dependent only on these time constants and nothing else? So that's an extra condition. That's actually a pretty strong condition, if you think about it mathematically. But anyway, so you can have these clusters, and so it means that these guys interact with each other, but they don't interact with the other things. And you can kind of tell from a circuit, right? So you can have a cluster of 3 capacitors in a transistor that are connected to each other and interact with each other. But if you have some buffers, like ideal buffers that are separating them, then that group will not interact with the other ones, right? You can construct something like this a little bit. This is a little bit of a contrived construction, right? You can have this, for example, and then you can have a dependent voltage source here driving a, let's say, I don't know, a transistor, so we can model it as like R pi, Gm, V pi, R2, et cetera, or something like that. And then you can have, for example, you have this capacitor here. You can have a capacitor here, here, and here. So in this arrangement, you can easily see that there's a single here and a double there. I mean, there are three time constants, but they produce a second order term. So that's kind of like a simplified version of that partitioning of the time constant. It's a useful thing. Now, how about the transfer constants? Now, the numerator can also be factored as well if this condition holds and you have h of n, let me use a different color. If you have h of n equals, so you have h, sorry, you have to have h0 being h of n being h of, or h of I, h of ij for, or yeah, h of n, h of ni, etc., etc. Actually, sorry, you just need the h of n, not h. H of n, h of ni, all the way to h of n, ij, etc., etc. And if you have that in addition to this, then you can actually factor the numerator as well. So the partition, zeros will partition too. That's a secondary thing. That rarely is, I mean, I don't use it very frequently. I don't know, maybe you use it. So that's one thing. Now, there are some interesting contrived examples that you may come and say, well, wait a second, this method doesn't work. Right? Sometimes I get something like this. So I'm going to make an example. So let's say this is your circuit. So that's for that discussion. But it's kind of like related, and it's a short discussion. So it's a question of let's say I make a circuit like this. Let's say we say this is our circuit. So this is V in, this is V out, R1, C1, and R2, C2. This is ground. Right? So what are the time constants for this? Well, there are two time constants. There are multiple ones, but zero value time constants. There's a tau 1, 0, which is R1, C1, obviously here. And then there's a tau 2, 0, which is R2, C2. And then what do we get? So, okay. So if I try to calculate my bandwidth, estimate my bandwidth, will I get a correct result if I just add the sum of the time? If you say B1 is the sum of the zero value time constants, this is true. B1 is the sum of zero value time constants, which is this R1 C1 plus R2 C2. But then I try to use it to estimate the bandwidth. Is this correct now? You can clearly see not. It's not. I can make this capacitor RC gigantic, and my bandwidth will be completely off. Right? I can make it orders of magnitude off by making this significantly larger than whatever this gives me, and this is going to be completely worthless. Now, B1 is still correct. But you say, wait a second, how's B1 correct here? How is that? Because we know what the transfer function of this thing is, right? The transfer function of this thing, even without writing time constants, is 1 over 1 plus R1 C1s. So that's the transfer function. And you say, well, how's B1 that? So there seems to be some inconsistency here, right? There's some problem, apparent problem. Because if I plug this B1 in here, it's wrong. But also, if you think about it, there's actually a B2, because there's now, for example, a tau 2,1, which is also equal to tau 2,0, which is also R2, C2. So there's a B2. So it also claims that there's a B2, which is R1, C1, R2, C2. So what's the problem? What's happening? Is the method wrong? Did something happen? This is a pathological example I'm giving. I don't like to starting with pathological examples, but I think it's important to understand the pathological examples at the end. Yes?
So there is 0 that cancels out.
Yeah, there's a 0 in this transfer function. Why is there a 0? Is there a capacitor, or is there an energy storage element, infinite value, yet you can infinite value and get a non-zero transfer function? Right, C2, right? If I short circuit C2, the transfer function doesn't actually change. So what you can write, you can say H0, which is 1, is also equal to H2. Right? Now, and that's the only H that's not, the other H that's, so H1 and H12 are 0, right? Because if you short circuit this, then you get nothing at the output. So what does that do in the transfer function? Well, it means that you have an A1 term, right? What is your A1 term? Well, more accurately, the numerator is going to be A0 plus A1s, which is, again, you can write it as H0 plus, now you have the tau 1, the H1 and tau 1, 0, right? No, I'm saying tau 2, 0. H2 and tau 2, 0 s. But now tau 2, 0 and H2 and H0 are the same, right? So I can factor it. I can factor H0, and I will be, so this would be 1. The ratio of these two is 1, so it would be 1 plus tau 2, 0 s in the numerator. And what do I have in the denominator? These two poles, actually, by the way, these two time constants, if you look at them, they're uncoupled, right? Because shortening or opening, so you can actually factor them as two different time constants. You can write the denominator as 1 plus tau 1, 0 s Well, this 0 becomes redundant if that's the case. Tau 2 0s. So you have 1 plus tau 1 0s, 1 plus tau 2 0s, and then these guys cancel, which gets you exactly to this transfer function. So it means that, yes, you can be clever about it and look at it up front and not do all of these calculations, noticing that this is not connected to that one or doing anything to that, so not taking into account. If you were a computer or acted like a computer and then just like did it blindly, like a machine, then if you are acting like a machine, you have to really be able to act like a machine all the way to the end. It means that having to calculate everything. Right? You can start acting like a machine and stop acting like a machine halfway through. Right? Basically doing something purely mechanical. But of course, but there's nothing wrong. I mean, this is what's happened. Now, this is an example of what they call it in control theory, observable and unobservable dynamics. So for this, so this is actually, so you can say, well, this part of the system or this system is observable or not. When you do control theory, actually a lot of discussion goes back to, well, this is unobservable, this dynamics. Right? So this is exactly an example of an observable part and unobservable part of the system. So that's called an unobservable pole and zero, or an unobservable dynamics in the system. Okay? Any questions on that? All right.